All right, let's talk about one of the most crucial and honestly most interesting parts of machine learning, feature selection. Here's the deal. Building a great model is a lot like making a great movie, and your features, well, those are your actors.
So, have you ever been there? You're staring at a data set with hundreds, maybe even thousands of features, and you're thinking, what do I do with all this? It can be completely overwhelming.
It's kind of like being a movie director who has thousands of actors showing up on set. I mean, it would be total chaos, right? It gets messy, it gets expensive, and the final movie is probably going to be a confusing mess. All those extra actors just add noise, and the real story in your data gets completely lost.
So the million-dollar question is, how do you sort through all those hopefuls and cast only the stars that are going to make your model a blockbuster? Well, that's exactly what we're going to break down. Let's explore 3 powerful strategies for choosing that perfect cast. Okay, first up is what I like to call the headshots approach. The more formal name for this is the filter method. Think of this as your very first round of casting.
So how do filter methods work? Well, they look at the basic stats of each feature and see how it relates to what you're trying to predict. And the key thing to remember is this is all done before you even start training your model. It's just like a casting director quickly sorting through a giant pile of headshots and resumes, just looking for some basic qualifications.
And that brings us to the big trade-off. The huge advantage here is speed. I mean, it's blazing fast, perfect for making a quick first cut when you've got a massive data set. But, and this is a big one, the disadvantage is that it completely ignores the chemistry between your actors. It has no idea if 2 average features suddenly become brilliant when they work together. So, when should you actually use this? Well, it's your go-to when you're dealing with a crazy number of features, you're short on time or computing power, or you just need a really quick, model-agnostic way to trim things down before you get serious. And the techniques you'll see here are probably familiar. You've got the chi-squared test, which is awesome for your categorical features. There's Pearson correlation, which is great for spotting those simple, straight-line relationships. And then you have mutual information for uncovering some of the more complex, nonlinear connections. All right, so we've sorted through the headshots. Now we're moving on to the chemistry read, also known as the wrapper method. This is where things get really interesting. With the wrapper methods, you're not just looking at resumes anymore. Oh no, you are holding actual auditions. You take different groups of features, you plug them into your model, you train it, and you see how well that specific group performs. It's all about testing the ensemble, the chemistry. Now, the advantage is pretty obvious. You can find the absolute best combination of features, capturing all those subtle interactions that can lead to some seriously high accuracy. The downside, it is incredibly time-consuming. I mean, training a model over and over and over again for every little combination, it gets really expensive really fast. And you've got to be careful, because there's a big risk that comes with this method: overfitting. You could find a cast of features that performs perfectly on your training data, that one specific scene, but then just completely falls apart when it has to deal with new data it's never seen before. So you really only use the wrapper method when accuracy is your #1 goal, and everything else is a distant second. It's best for data sets that are a manageable size and when you have plenty of time and the computing budget to let it do its thing.
Some popular techniques you'll see here include recursive feature elimination, or RFE. That's where you start with your full cast and then, one by one, you remove the weakest performer. Or you can do the opposite with forward selection, where you start with nothing and add your best actors one at a time. And of course, there's backward elimination, which starts with everyone and whittles it down.
This brings us to our third and final strategy, which is honestly a really clever balance between the first 2. Let's meet the onset director, also known as the embedded method. Embedded methods are just so efficient because they combine the casting and the rehearsal into one single step. The feature selection happens during the model training process. The algorithm itself is smart enough to learn which features are important and which ones are just taking up space. So it's kind of like a director who hires and fires actors right there on the fly during rehearsals. And this gives you a really smart balance. Embedded methods are way more efficient than those slow wrapper methods, but they're still model-aware, so they understand feature chemistry, unlike the filter methods. The only real drawback is that they're director-specific. The selection process is tied to a specific model, so the features a lasso model loves might not be the same ones a random forest would pick. This makes embedded methods a fantastic choice when you're looking for that perfect sweet spot between performance and efficiency. They're ideal when you're already using a model that has this built right in, like tree-based models or regularized regression. Some of the big stars of this approach are things like lasso regression, which actually shrinks the importance of bad actors all the way down to zero, basically writing them out of the script for you. And then you've got tree-based models like Random Forest, which can just give you a ranked list of which features contributed the most to the final story.
Okay, so we've met our 3 casting directors. How in the world do you choose the right one for your project? It's time to make the final cut.
So let's just break it all down one last time. You've got the filter method, our headshots. It's the fastest, but its accuracy potential is a bit lower because it's model agnostic. Then there's the wrapper method, our chemistry read. It's the slowest by far, but it has the highest potential for accuracy. And finally, the embedded method, our on-set director, giving you that fantastic integrated balance of both worlds.
And here's a really simple way to decide. 1. Is speed your absolute top priority? If so, start with filter methods. 2. Is accuracy the only thing that matters and you've got the time and resources to spare? Go for wrapper methods. And 3, for just about everyone else who needs that smart, efficient balance, embedded methods are probably your best bet.
You know, in the end, choosing the right features isn't just a technical problem. It's really a blend of science and strategy, of understanding your data, your goals, and your limitations, just like making a great movie.
So I'll leave you with this question. For your next project, what role are you going to play? Are you going to be the fast-moving casting agent, the meticulous audition director, or the balanced on-set director? The choice and the final cut is all yours.